This video is going to look at section 1.6 of A Level Chemistry for AQA, which is chemical equilibria, specifically looking at dynamic equilibrium. The video is going to cover reversible reactions, dynamic equilibrium, and basic graphs for equilibrium. So to start off with, if we were to take salt, just plain good old sodium chloride, and add it to water, the salt will dissolve. If we keep pouring the salt into water, will it keep on dissolving? Eventually, we would get to a point where the salt appears to stop dissolving. We'd see a pile of salt appearing on the bottom of the beaker, and eventually it'd separate out, and no matter how much we stirred, we wouldn't be able to get that salt to go away. And that's because it's a saturated solution. Now, we're just going to have a quick reminder of what a saturated solution is. In our example, we have water, which is the solvent, and we have a solute, which in our example is the salt. And when the solute dissolves into the solvent, we get a solution. Just have a quick think about the particles and what happens when that occurs. The reason we get a saturated solution is because the solute breaks down into tiny parts, into its constituent ions in this case, and fills up the spaces between the water molecules. We get to a point where no more solute can dissolve and fit in those spaces between the solution molecules, in this case water. And that's what's happened here. We get to a point where no more salt can dissolve and fit into the water. But I use the term appears to stop dissolving. So we need to think, what is actually happening? And if we think through the chemistry, sodium chloride is ionic, and that means that it will dissolve in water at standard conditions. If you put something ionic into water, it will dissolve. This means that the solid salt at the bottom of that beaker will continue to dissolve in the water, because solid ionic substances will dissolve in water. But for that to happen, some of the already dissolved salt that's in the solution has to crystallise and turn back into a solid. Now the salt only appears to have stopped dissolving because the rate of dissolving is equal to the rate of crystallisation. So obviously it's happening on a very, very tiny scale as well, so we can't see this happening. But the continual dissolving and crystallising process is still occurring. We just don't notice a change. So this salt dissolving and recrystallising process is an example of a reversible reaction. The solid salt is turning into dissolved salt, but the dissolved salt at the same time is turning into solid salt. And we can get progressively more chemical with this. We can say the solid sodium chloride is turning into sodium chloride in solution and back, or the NaCl solid is turning into NaCl aqueous and vice versa. Now you've probably seen this reversible arrow before. The two-way arrow, as shown, represents that the reaction is a reversible process. It can go forwards and backwards. So we can model this using a piece of tubing, for example some guttering pipe. The tube would be filled with tennis balls end to end, just like that. What would happen if we tried to push another tennis ball into this tube? Now as we push the tennis ball in, a ball would pop out of the other end. And as fast as we push balls into one end of the tube, they will pop out of the other at the same speed. Now the number of balls inside that tube does not change, it remains the same. As long as we are pushing the balls in at the same speed as they're coming out, the number of balls inside will stay the same. And that models our salt dissolving in water. As long as the rate of crystallising and dissolving is equal, the amount of solid salt remains the same. Now the process of the salt dissolving and crystallising, all the tennis balls in the guttering pipe being pushed in and coming out, it is an example of a dynamic equilibrium. Now the amount of salt in both the solid and solution state remained constant, as there was a continual change between the states. So there is a definition that you need to know for dynamic equilibrium, and the definition is that dynamic equilibrium is when the forwards and backwards reaction rates in a closed reversible system are equal and the concentrations of all species, both reactants and products, remain constant. Now the dynamic part specifically refers to the fact that the reactions are continuing. So that's not part of the definitions, but it's just implying that this is a system that is continuing to react in both forwards and backwards reactions. It's not stopped. Now also just to point out, a closed system is something that prevents reactants or products escaping, for example a sealed container. Now that would often be used in industry, something that is closed and literally cannot allow anything to go in or out. The final thing just to mention is that equilibrium can be written using shorthand symbols of 3 horizontal lines followed by a subscript m, and that literally does just mean equilibrium. So if you see that written anywhere, that's what that means. Now we can represent equilibria using graphs, and here's a very simple example showing the rate and time for a reaction, A plus B, forming C plus D in a reversible reaction. And I've got a couple of questions for you. Number 1, which line, the red or blue, corresponds to the forwards reaction? Number 2, explain how you came to this conclusion. And number 3, whereabouts on this graph shows the point at which equilibrium has been reached? So pause the video and have a think through those questions. Now to go through the answers, the line that corresponds to the forwards reaction is the red line. And the reason for that is that the rate of the forwards reaction would always be very high at the start, as you have the maximum amount of your reactants, in this case A and B. And we know that high rate of reaction is caused by high concentration. Now as the reaction progresses, A and B turns into C and D. So A and B will go down and C and D will increase. So the blue line shows that we have the backwards reaction, because that will be 0 at the start, as at the very beginning there will be no C and D, so there's no rate of reaction. For question 3, where on the graph shows the point at which equilibrium has been reached, we need to think about the definition of equilibrium, which is the point at which the backwards and forwards reaction rates are equal. And for this graph, that will be where we've put the X.